Is it recording? Okay, so the first things first is everybody get into DCC on demand, logging in and whatnot. So does everybody have that open and they're in DCC? Thumbs up from people, thumbs up. I'm assuming everyone on Zoom has that. And then we're gonna basically pool. So go into Git, click on pool, and this is gonna refresh everything. There may be some changes. Let me know if there's any problems with that. I went through basically last time and I've kind of renamed a lot of the lectures to kind of have them line up numerically. But hopefully that works fine when you pool. Today, we're gonna kind of finish off some of the material that Josh wasn't able to get to. I think he didn't get to the graphical summaries. So I'm gonna pull open that R Markdown. And basically what we're going to do, so it's, now I think it's marked as 11_day_5, that R Markdown. So I'm going to go down to graphical summaries, right? And so we're going to go over these different approaches that you may use. So to kind of, I'm going to run all the code above to get to get everything up to date. So I'm basically going to just click on this little button that says run all chunks above. And so this is going to take a little time. But while this is running, don't forget to go do the sign-in sheet and whatnot at the top. So as a reminder, the sign-in sheet link is basically at the top of the document. And then you just go to the column with today's date. If you could put an X there, that'd be great. Okay. All right, anybody have any trouble like running all these things above and getting up to date, up to where we are? Okay. So we're going to be kind of going over a couple different graphical summaries. So first off, we kind of talking about bar plots. These are pretty commonly used for, categorical data to show how much in each different categories you have for, say, either a nominal variable, so something like, say, gender identity, or say more ordinal category, maybe like years of post-high school education or something like that. Often it's characterized by kind of the spaces between the bars, the height of the bar, and then the width of the bar. So we're going to look at this case one and basically look at the, do a bar plot by the self-reported race. So we're going to do case one, we're going to select pub ID, publication ID, raceful, and we're going to drop missing levels. So this is going to drop in A's, and then we're going to drop if there's any levels that are completely missing. So that's going to give us our tibble, right? There is going to have a pub ID, it's going to have the race that was reported, and so on, all right? And if we want to see what that looks like, so if we take a sample of that, say slice sample, you're going to get a different set of 10 individuals. And we can see like, okay, this is what this kind of looks like. So we have 10 people and, a few of them self-report as white, a few self-report as Black or African-American, one self-reports as Hispanic. All right. So to basically run this, what we do to do a bar plot is you first have to summarize and count how much information there is in each of those races, because you pass that count information to a bar plot. So we go mode T, group by race, and then count. So this part right here is going to basically give us a breakdown of the self-reported race and ethnicity by each group. So we can see we have 32 individuals who identified as Asian, 399 that identified as Black or African American, 9 as Hawaiian or Pacific Islander, and so on. Okay. So once we have that, it's then piped and passed down to ggplot. Okay. And so within ggplot, we're passing in the race information, and we're going to give it what this is doing is telling it to reorder the race variable by count, so it'll show up in kind of a nicer, readable, from smallest to largest, or maybe it's largest to smallest. And then we'll tell it to do some colors. We're going to say fill gray, color black. We'll give it some text, some labs, and then the scale. Okay. So GM call is the bar plot. So when we do that, we get this bar plot where you can see it's ordered from from say the least self-reported to the what was the most reported race ethnicity within this group. Okay, and so that's using the GM call. Sorry, GM call is not the color we're passing it in. So that's the bar plot basically. So if we said hadn't done that reorder, what would have happened is it would have just kind of reordered it alphabetically. Right, so then so you can see like white, then other race, Native American, multiracial, Hispanic, Hawaiian, and so on. So that reorder was just kind of reorganizing our race variable by frequency to kind of give it a nicer visualization. Does that make sense? Any questions so far on that? No. Any questions on Zoom? No? Okay. All right. So we'll do this again, but now we're going to show the percentage. So I'm going to do mode T. And this time I'm going to, instead of count, I'm going to use summarize, right? They're going to give us the same thing, but, let's just see how many different ways there are to calculate these things. All right. So once we have that, we have our data frame again, right, with the N for each of the self-reported groups. And then we're going to calculate the percentage. So we're going to go mutate percentage, and go take the N and divide it by the sum. And we're going to round it to 1 digit. So we get that. We now have, okay, 1.3% of the group identified as Asian, 15.9 identified as Black or African American, and so on. All right. And now we pass the ggplot, and instead of the N, we pass the percentage. And so for people, I didn't mention this, but the geom text is just adding the percentage text at the end of the bar plot. So now if we do this, and then the scale Y continuous is just kind of adding some space for that text. We get it by frequency, and so you can see the frequency of each of them. So we have 0.3 all the way to 69.6%. All right. So these are some of the ways when you have, say, a categorical variable that you may want to think about trying to summarize and visualize it. Is, say, you're tired of having too many tables, right? And you want to throw a figure in there. People love figures. I think they hate tables. Okay. Any questions before we move on to histograms, which I think we've probably already talked about a bit. So histograms are the continuous analog of the bar plot. So we're looking at the continuous data and seeing what the distribution of it looks like by frequency based on some, kind of finer categories that we have. So there's no spaces kind of between the bars, and you have to be kind of thinking about what the pattern is and then whatnot. So the shape, where the center is, the spread, and whether or not there's potential outliers. So I think you already kind of looked at this, right? Because Josh did the stuff about asymmetric distributions, right? And everything, you're looking at the histograms there. And for ease, you always want the width of bar to kind of be the same to help with visual interpretation. All right, so we're going to take the case 2 data set, and we're going to do log10 viral load. So we go ggplot, go case 2, pipe command, AES, and we say log10 viral load, and then we say geom histogram, and then we give it some labels, and I put theme black and white, because why not? And what we see is this histogram of log10 viral load, right? Within this data set. So what are, what are some immediate things that kind of jump out at you looking at this?
You don't really know.
Yeah. It's a little messy. It looks a little skewed, right? Seems to have a left tail. There's maybe some, I'm kind of curious about this. The mass of people are all the way at the end. Is that some kind of boundary issue with like regards to the machine itself not being able to measure past whatever 10 to the 5th is, you know, for a viral load? So, you know, there's some things that are kind of popping out, you know, kind of looking at this. But yeah, the data's skewed. There seems to be a lot of variability. And then there's also a lot, you know, there's maybe some boundary issues. And there's definitely going to be boundary issues at the bottom as well, right? Because we know that once people are controlling their viral load, undetectable, right? People usually put, oh, it's less than 50, you know, or something along those lines. Okay. All right. So we're going to now repeat this, but now we're going to do it basically by gender, by what they identified as. So we're going to do case 2. So within that data set, gender, when it was marked as 0, represented someone who identified as female. 1 represented someone who identified as male. We're going to pass that. So we're basically making this nicer label, right? So otherwise it's just going to be 0, 1. Same thing, geom histogram, and now we have that facet wrap command, right? Which will facet it and go over it, everything. Go like break it out by the categories. So we run that, and now we get the breakdown by, we have the people identified as female on the left, and the people as male on the right, and we can see that skewness again. It maybe think maybe it looks a little bit of a bell shape or something in the females, but it's like if you look at data enough, right, you're bound to see patterns even if there really isn't any. So, okay. Any questions about histograms? They're very useful for getting an idea of the distribution of the data, kind of at the beginning, and then especially for comparing between 2 groups. Okay. All right, so next up, box plots, or what are they, whiskers? People call them whisker plots or something like that. Yeah. 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 So this is going to be kind of a graphical display, and it shows kind of the median, the 25th and 75th percentiles of the data, and extreme values. So the boxes represent the 25th and 75th percentile. The center line is the median. And then, you know, the whiskers are going to be 1.5 times the IQR. So remember, the IQR interquartile range is the 0.75 minus 0.25. And then values outside of 1.5 times are often marked as outliers. So we're going to take that case 1, and we're going to look at age. So we do case 1, DF. So implicitly, we always kind of write just AES, but really it's assuming that that's the mapping item within the ggplot. So if you look at ggplot, it has like data, mapping, ... the environment. So that's what we're passing to it right there. We go geom box plot, and then we'll give it a title. So this basically shows us the box plot by age, which sometimes, you know, is useful, sometimes not, right? So what I more use it for, right, is when you have some other categorical variable and you want to look at that quantitative distribution, quantitative variable, and compare by that categorical variable. So if we do case 1, df, ggplot mapping, and we say x is equal to treatment, it'll now give us basically the box plots broken down by our 2 treatment arms, placebo versus vaccine, and the age on the y-axis, right? So this is kind of a nice and allows for some comparisons, right? It's a very simple visualization. Now you want to be careful about this. So let's see. What is I'm sorry. Fine. All right. So you always want to make sure you pass in a categorical variable. So let's say I put in, BMI here. Oh, that's interesting. I wasn't expecting that. So it actually, okay, I was expecting it to kind of break it out, but it doesn't behave the way I thought. So never mind. Ignore this example. But let's see. If we did as.character, I think it would perform as I expected. Yeah, this is where it's going to get messy. So never mind that you can kind of ignore this. So this is only going to happen if you do kind of something stupid. Not stupid, but you just kind of do the data as is. So if you pass in as.character BMI, you have age, you'll get this kind of mess because it's going to treat each individual unique BMI value as a new category. Okay. So as a question, should there be differences in age by study arm? This is going back to this, remember that case 1 was a randomized trial. Oh, no. So would you expect there to be any differences by age?
You say, would you expect any differences?
Yeah. No, right, because it's a randomized trial. So in general, that means that, these kind of baseline variables pre the vaccine or the treatment shouldn't vary by treatment. Okay. So if you want, we can say, look at this gender label. We'll do case 2. We'll do the gender, and we'll do the log 10 viral load. Right, so the X is equal to gender label, and it will give us kind of the breakdown of the log 10 viral load by gender. So we have the females and the males. Okay. So what pattern in HIV and RNA can you see in these plots? Or do you think that you see?
There's a difference, like with the female, I think that's like the top and bottom out signature more of them.
Yeah. There seems to be some outliers, more outliers, right? So these are, the dots are outliers. And if we go back up to the histogram, you remember, right, there's all this data out here to the left, right? And the big portion of the data is here. Sorry for the people on Zoom. I know I'm pointing at a screen, but this is how it is. Anything else that you notice from this?
Other than like the box, like height on the outside a little bit smaller.
Yeah, there's maybe the IQR is maybe a little bit smaller for that, right? Maybe what that's saying. And it looks like it's maybe a little, the median's maybe a little bit higher in the males than versus the females. But again, these are just kind of looking at the data. We're not doing any statistical tests or anything like that. So, okay. So some cautions on box plots. They are very useful, but they're not going to always be sufficient. They're limited by what they can display, right? They can display those 3 things. The outliers, sorry, 4 things. The outliers, the IQR, and the median, and your quartiles. So there may be cases, right, where they may not be sufficient. You maybe want to couple them with the histogram. So this is going to be kind of a generic example. I'm going to generate 2 data sets. one from a normal with mean 0, another from a normal with mean 4.5. And I'm going to pass this to ggplot, box plot, right? And it looks just kind of fine, right? But it's not going to be able to pick up on if there's like a bimodal distribution in the data, right? Like in this example, right, half of the data has mean 0 and half has mean 4.5. And in this, that's just going to look like it's just going to come out in a wash and look like it's, you know, maybe potentially symmetric. What you can do to get a look at this is if you plot it again and you add this geom jitter, and you should really add a seed here. I think you can add a seed. No, maybe you can for geom jitter. So what this will do is kind of overlay the points on top of the box plot, right? So you can see it like, oh, it looks like there's a big mass here, and then it looks like there's a big mass up here. So maybe there's two separate distributions. The other thing you could do, right, is look at the actual histogram. So we'll just use the histogram function here, the base histogram. And so if we plot that, let me see this. You can see that kind of dual distribution. So this first bit is plotting the histogram, and then this is adding kind of a density, an estimate of the density of the data. And you can see that bimodal distribution of the data, right? So box plots are incredibly useful, but again, there's some things that they're not going to be able to pick up on. Any questions on that? Going to violin plots. Okay. So this is a kind of a combination. I'll show the box plot along with the density curve kind of overlaying it. So the density curve is a non-parametric estimate of a probability density function, which we'll get to in the later parts of this lecture here. So if we take that data again, right, this kind of messy data set, well, you know, that's half from mean 0 and half from mean 4, I believe. And I'm going to basically make it into a tibble, so I can just pass the ggplot. I'm going to say AES, x equals x, y is that. So I'm giving it a fake x variable here to use, right? So if we look at this, I basically just added this fake x variable for the box plot, which I don't think we actually need now that, you know, based on some of the earlier examples. So if we do geom violin, we do geom box plot, this will kind of, it overlays, so we have the density, the estimated density here, right? So you can see that bimodal. And then on top of that, we have the box plot, right? So this is kind of a way to combine it to get an idea of what's going on in the data. Any questions on box plots and violin plots before I move on? I'll be honest, I don't use violin plots that often. Usually I think a box plot and histogram can suffice, but some people, you know, it definitely can help, right? And overlaying everything into one plot. Any questions on Zoom? All right, no? Okay, so next up, scatter plots. So scatter plots are basically taking two quantitative variables and plotting them against each other. And they have to be paired in some way, right? So, you know, I have a height, I have a weight, everyone has like two continuous variables, right? And so the x-axis gives one value, the y-axis gives the other value. And, you know, we typically sometimes think of them as like one being the predictor or the independent variable of interest, right? That we're trying to say something about the y variable about. So it's helpful in identifying the direction of association, potential clusters of data, and whatnot. So we're going to look at case one, and we're going to look at age versus BMI. So the way we do this is we take case one, We pass it to ggplot. We're implicitly kind of saying here, X is equal to age, Y is equal to BMI. And then we just put geom point. And then we can give it a label, right? So title, subtitle. And then I'll give it the black and white thing. So I'm gonna run this. Control enter, we'll run that bit, and then control enter, we'll run that. And we can see kind of the relationship where it doesn't really look like this much, right? And this is something where age, right, isn't, the way it's measured isn't strictly 100%, continuous in this case, right? Because it's like, well, we're not getting values of 21.5, right? We have 20, 21, 22, 23. So that's why we get this kind of what it looks like here, where it has these kind of bars with little breaks between them. So is there any trends in this? People observe? Sometimes it can be no. Yeah, so it doesn't really look like there's much. You can maybe say like, oh, this is a little higher in the older, but it's really, you're just kind of staring at one of those magic eye plots, right? If you look at data long enough, you're eventually going to see a sailboat or something. Okay, so let's do this again, but now we're going to look at weight and the HIV RNA, right? The log 10 viral load. So same thing, go weight, log 10 viral load, and then plot. So this is in case 2. And we kind of get this basically. So we can see there's definitely some boundary issues up here, right? Where it looks like you see all these values kind of clumped up at the top. So that must be a part of the assay, right? Where it can't maybe give you a value above a certain threshold. But again, it doesn't really look like there's any patterns, really. I mean, maybe a little bit like larger weight, lower log 10 viral load, but I wouldn't want to write a paper on that. All right, how about anybody have anything on Zoom? Do they think if they see anything? Yeah.
An outlier versus the population of like 30 to 75.
No, in this group, maybe a little. Yeah. And so, a little bit more than the other one for sure. So next up, we can look at basically, we can add color to scatter plots, right? So we can remake that plot above, but color it by the gender. So, we'll make this gender label variable again, and we go weight, log 10 viral load, and we go color equals to gender label, geom point. I'm going to give it this custom palette. So this is going to be the dark 2 palette, the label. And now when we plot it, we see it broken up like where it's colored by gender, right? Which is nice. All right. And on the same thing, you can add, like say, best fit lines to this. So repeating this for gender, we're going to add this geom smooth, which is going to and we're going to say method equals LM. So it's going to add a linear model via like a standard regression, which we'll talk about more in the workshop series 2 in the, I guess it's winter, but January, spring. And what this will do is add the best fit lines to the data, and it's going to do it by, I believe it does it by gender. So if we look at this, we can see the 2 different lines basically fit. So one's fit to the male subgroup, and the other one's fit to the female subgroup. Right, and you can see the kind of tealish line, the kind of orange, green and orange lines. Okay. And if we had basically, if we had put standard error is equal to true here, it would kind of put some little like confidence intervals around it. Like, this is what we think it would maybe be. But we'll talk more about confidence intervals later on in this session. Okay. So next up, we're going to talk about matrix plots. So these are basically a way to just plot a ton of, if you have a ton of continuous variables and you just want to plot them together to look for any bivariate relationships. Bivariate means two variables, right? This is kind of how you can do it. So this can be very useful, right? If you have a ton of continuous variables, or say if you're working with a bunch of immune data and you want to look at how all these different antibody assays may be paired together, this can be a way to kind of summarize it really easily. So this is just going to be a function that I'm going to now pass into this pairs package. So basically I say, all right, pairs, I'm going to give you 4 variables. There's a little formula, log 10 viral load plus age plus weight plus CD4. This is the panel, this is the data. PCH is the symbol basically. So we go PCH and R. We can look at, I never remember any of these. So it's going to give us a filled in circle, right? And if we do this, right, it's going to give us a kind of what it looks like, and it has this lowest curve over it. And so you can kind of get an idea of the overall distribution between the groups. And if you press on this button right here, it'll pop it out so you can maybe see it, and it looks a little bit nicer. So it's like, okay, maybe age, weight, but you know, again, it's just kind of a real quick and dirty way to kind of graphically summarize the data. Right? Okay, any questions on that before we have some exercises? No? Okay, looks like no questions. So, so look at the variables in case study 2. We're going to look for outliers, any weird odd values, coding this section, and we're going to look at basically visualizations for each of these. So I already kind of have the code there, so we'll just kind of go through it. So I'm going to take this case 2 data set, and I'm going to select the variables I want: age, weight, viral load, log 10 viral load, and CD4 count. All right. And what I'm going to do is basically make this these kind of panels of plots over and over and over again. So, and then I'm going to fill it in. So we take this. So we're going to have this basically empty vector, and I'm going to fill it in with plots to then print. So I'm going to basically loop through the columns, and I'm going to say, all right, take this column. So you're going to be 1 through 5. We're going to basically omit any missing. We're going to do a histogram. We're going to do a density plot. We're going to do a box plot. And then we're going to return that in there. And then we're going to do this cow plot to kind of plot it. All right. Any questions on that? It's kind of a combo. It's a tricky way to do this, but this isn't something I would expect people to like be able to write this up really quickly. There'd be a lot of Googling to find out how to write this up. Okay. I'm gonna run this. It's gonna run. It's not gonna give us anything yet. And then I'm basically going to now do this plot grid, and I'm going to give it the plots to. So now if we look at like all plots, it's this big list, and then it's going to just kind of dump them one by one, and I'd have to go like, okay, here we go through it, which isn't really nice. So I'm going to say, all right, plot list, all plots, one row, and align it kind of horizontally. So now what this is going to give us, it works, come on. There we go. So this is basically showing us the data now kind of across the plot, right, for each of the variables. So, all right, I'm just going to run all of this all at once. And we're going to get basically the different distributions. So we have for age and weight, this shows the weight. This shows the, I believe this was the viral, log10 viral load. No, just the viral load, the log10 viral load, and then the CD4 count, right? So this is kind of to just look at it and say like, okay, CD4, are there people that have 0 values of CD4? That may be odd. Maybe we want to ask about that. Go see who collected the data and be like, hey, is that right? We look at it, we can then look at the data set, which I think we called DF Explore, Data Frame Explore. We can go, okay, filter. What I'm gonna do is I'm gonna go slice min CD4. And we can say, oh, that's interesting. This is a person that has 0 CD4 counts. Is that right? Or is that some kind of weird coding thing that's going on? Right, so this is maybe a way you can kind of look at the data and say like, all right, what's going on here? Is there problems with the data set? Is there stuff that we want to follow up on? Like maybe this is not a person that's controlling, right, our load, but I still don't know if their CD4 count should be 0. There may be people who have a little bit more HIV AIDS research than I do. Is that possible? Or are you?
I don't think so.
You don't think so? Yeah. People on Zoom, anyone know? Is that can someone have 0 CD4, or is that basically? You think yeah. Great. All right. So, question 2, we're going to basically create a bar plot showing the percentage within each BMI category that received the vaccine. We'll drop people missing BMI. So I'm going to take this data frame. I'm going to drop those that I'm going to keep only those people that have non-missing. So this is basically filter, and remember the exclamation point says not. So it's like an annoying kid joke, like not missing BMI. We're going to group. We're going to count. Actually, here you don't actually need the group. We could have just, actually, no, here I think we do. So group by BMI category and treatment. So I'll just kind of show you what this is doing so far. So we have, for each of the BMI categories, we have the treatment and we have the count for each of them, right? And what we're going to do is, because it's grouped, we're now going to calculate the percentage. Because it's already grouped, the data is going, when it does the sum over n, it's only going to sum within that group. We do that, and now we have the percentage within each of those groups. And if we sum every 2 percentages, it should come out to basically, it should come out to 100%, right? And then, because it's kind of redundant, we can just filter to those that have vaccine. Right? We don't, if you know the vaccine treatment, you know the placebo treatment, right? You know how many got the vaccine, you know how many got the placebo, because they have to sum to 1. And then we'll just plot. And we'll do the geom call for, the bar plot. And so forth. So we do that. Plot by percentage, we'll basically have the breakdown of how many received the vaccine within each of the BMI categories. So in the BMI greater than 40, about 47% received the vaccine, in that kind of 18.5 to 24.9, 48.4, and so forth. So here I have it ordered by percentage, right? But this is a case where maybe, you could say maybe it makes more sense to order this by the BMI, right? Because there's a natural order to the BMI categories here. But just for the sake of this example, we use the percentage. And you can see here, it's getting cut off a little bit. So if we went back, I'll steal some code from up here. I'll add this. So basically I'll add plus scale. I'm going to add some limits to the y-axis. And now we'll kind of get some more space out here so that it doesn't get cut off. Okay. All right, so that's the end of kind of wrapping up last week. So let's go ahead and take like a 5-minute break, and then we'll go into the next session, 5 minutes. And so that's going to be this 12_day 6. And here we're going to be getting into more kind of statistics and probability densities and whatnot, and talking about actual distribution. So there may be some math, but don't worry. So, okay, great. Go ahead and, yeah, we'll go ahead and take a little break. Recording again. All right. We're back. We're going to talk about this, and so we're going to basically, set some paths using the here package. Josh gave me some guff because I wasn't using it. So these are just going to be some paths to where the data is located. All right. Okay, we can skip the sign in. We did that already because we were talking about we finished off day 5. Okay, so within the case study 1, we're basically going to take a little bit additional data on risk factors for HIV that they have within the data set. So we're going to first read the data set. So I'm going to specify the path. So case 1. So now we have data set. Bring it too much. That has basically the treatment, publication ID, and all this additional stuff. We can get the information on, what the dictionary risk. So if we look at that, it's basically giving us information on what all of these variables are, right? And what maybe the risk is. So if it has HIV male partner, unprotected and serious anal sex, had a female partner, exchange of sex for money and gifts, crack cocaine use, and so on and so on. Okay. And basically what they had in the paper is they calculated a risk score based on those measures that we're going to look at. So it's going to be this variable, this data frame here, case 1 risk. So we can see it has this kind of information, and we can see, well, so the risk score I think is in the major file, but you can see it's like marked as 1. So, this is maybe someone who maybe exchanged sex for money, and so on. And then if we wanted to look at the actual dictionary, so this is maybe something, if you were making a report, you'd pass this out to Cable, and it'll kind of give everything broken down. And it tells us like, okay, 1 is yes, 0 is no, for each of these variables. Okay. This is the data frame. So you can see the hash. And come on. And we're going to now join our main data set, this case 1, with this DF case 1 risk that we just read in. Okay. So we're going to do case 1. And it should just join by treatment, pub ID, and TRT, right? Which those should be uniquely identifiable. Okay. So these individual risk values, so they do have a risk score here. I'm just going to read from this. So basically for inclusion of kind of the risk, it was an indicator if the number of male sexual partners was greater than 3, and an indicator of unprotected receptive anal sex. The risk score was calculated as a weighted sum of these 2 risk variables, each weighted by an estimated hazard ratio. The risk score takes a value of 0 if a participant had neither risk factor 1 if they had both, and an intermediate value, 0.46 or 0.54, if they have one or the other. So there's some like math going in and around in the back that you can go and look at the paper if you want to get like a better understanding of how they calculate it. We're just going to kind of use it as is for now and not dig too deep into it. And so, I'm sure they had a lot of very smart people working on this. So, it's likely all right. Okay. Case study 2, read that in. We'll calculate the log 10 viral load. We'll do basically, whether or not it's at a lower limit. And then, we talked about this, the person that has 0 CD4 counts. It is
very rare, but
it is possible. All right. Well, we're gonna remove this person for now. So basically, we're gonna say if any of their viral load values. So basically, we're gonna take this case 2. We're gonna group by SID, and we're gonna say if any of their CD4 values equal to 0, drop them from this study. So if we didn't have that filter, this thing here, it would just give us that one, that one person, right? So we're gonna drop this and then we're gonna ungroup. We're gonna just take the follow-up data and we're gonna kind of summarize basically on how many are undetected versus, looking at undetection. So basically, if a person is ever undetected in this data set, we're going to mark it as 0, and then otherwise 1. So, and then we're going to merge it with the baseline data. So we're going to take this case 2 data, filter to time 0.10. We're going to select the SID and non-adherence, and then join with this data set that we just made. We look at this. Basically tells us, okay, looking at whether or not they were controlling. So we can look at this again. So we look at case 2, follow up, we'll just look at filter where SID equals 1. So we can see for this person, right, while there was a point where they weren't controlling, the vast majority of the time, right, they were potentially controlling their viral load. Well, if we look at, say, SID 11, so actually, okay. Oh, so sorry, so this is, I got it mixed up. So this is someone who was controlling the entire time versus someone who wasn't controlling. So this person up here, there is a point at which they did not control, right? While this person with 11, which has a 1, controlled the entire experiment, the entire trial. Any questions on that? Okay. And then I'm just going to drop this because I don't want it hanging around. All right. So some definitions. So we're going to talk about what a population is. So this is some collection of elements, right, of interest. We're often thinking of humans is what we're interested in, but you could break it down further. It could be like humans within North Carolina, humans within the Research Triangle area, and so on. A variable is some characteristic of the people within that population that varies, right? So height varies, hair color varies, age varies, our CD4 counts vary. There's quite a large collection of things. A random sample is some subset of potentially independently and randomly selected elements from that population, right? We can't go out and measure everybody in the Research Triangle CD4 count, right? That's not practical. But we can maybe collect a random sample of some population of interest within that, right, and measure it. And then the hope is that that random sample is representative of the population of interest. A random variable is some characteristic that takes different values for different elements within your sample. And the sample space is what are the actual possible values that that random variable can take, right? So if we're looking at weight, it's not possible for someone to have negative weight, right? They can't have like -2 kilograms, right? So an event is maybe some kind of subset of interest of the possible outcomes in the sample space. So that could be, say, a death or maybe a BMI above a certain cutoff. And the probability is, say, the relative frequency of an outcome to all possible outcomes in the sample space. Usually it's denoted, so we're getting into some math. It's like Y belongs to A. So this epsilon here is sometimes used in math speak is like belong. Like where Y is some random variable and A is a subset of the sample space. So for that BMI, A may be like BMI greater than 20, right? So Y of 25 belongs in that sample space. A Y of 19 does not. Okay. I'm going to switch to visual mode because I think if I recall correctly, there's some nice visuals in this. Actually, I'm going to switch to the HTML document real quick, and we'll switch back and forth to when we're running code versus when we're looking at some of these more text and math and whatnot. So let's go into data sciences, go into lectures. So this is going to be a little annoying because it's this HTML document. I'm going to download it, and then I'm going to ask it to open in Firefox because I don't like Edge. Okay. So this is what the compiled document looks like. All right. So we have our probabilities. And so let's talk about our case study 1. So to be eligible for that study, the men and transgender women between the ages of 18 and 50 years were required to be fully circumcised, to have a history of unprotected anal intercourse with one or more male-to-male female transgender partners, or anal intercourse with 2 or more male or male-to-female transgender partners in the 6 months prior to randomization. They're required to have negative HIV testing and to have a adenovirus serotype neutralizing antibody titer less than 118. And I believe that's trying to skip that they haven't been exposed potentially to HIV, right? And then to have an alanine amniotransferase level of no more than 2.5 times the upper limit. So the variable here may be, say, like, what is the body mass or height of these individuals? And then we may randomly select 300 individuals, may measure the BMI, and then we look at the kind of the sample space. So for BMI, what is technically the sample space, right? It could be 0, it could be all the way up to infinity. And we want to know what's the probability that someone has a BMI greater than or equal to 25. And so that's what we're going to estimate. We're going to estimate that probability. Okay. So go down here. So we can look at the data basically. So we look at the mean BMI. Okay, hold on real quick. Oh, it doesn't like the visual mode. There we go. I'm going to switch back to source. All right, we're going to take the mean and the standard deviation. Remember, the mean is kind of a measure of centrality. Standard deviation is a measure of spread. And we're going to kind of plot, say, what a normal distribution of this kind of data looks like. So we're going to say, we're just going to make it kind of a blank thing for now. And we're going to pass it this D norm, which is the density of a normal. And we're going to give it the mean and the standard deviation. And then we're going to kind of plot it and to basically see what the area and look at kind of a probability density function of this kind of data. And we'll talk more about probability density functions later. Okay, so there was some non-missing. So what we have here is the black line recall correctly. Yes. Okay, so the black line is, say, like what a standard normal looks like, right? A normal distribution. The blue line is what we actually observed in our data set, right? So it may not be normal. So this is kind of just giving us an idea, right? This is what the data set looks like. And we could kind of simply do that. And if we, some people like to transform the data. So if we look at like log 10 of BMI, maybe a little shifted, maybe a little bit more bell-shaped, but not necessarily. Okay. Any questions on that? We'll get at the actual like probability that, say, a BMI is greater than 25. Any questions? No? So I mean, no questions on Zoom? Okay. All right. So in case study 2, we basically have HIV-infected patients at a wellness clinic in Bella Bella, South Africa, from 2005 to 2009, right? It had to be 15 years or older. So this is all going to the public domain. This is their population of interest. And the variable of interest was whether or not virological control over the follow-up period was, that they maintain some control of that viral. And they had like 320 individuals, let's say. So what's kind of the random variable here? Well, so there's some specific thing about the individual, though, that we're interested in this case. Well, so the variable, right, is whether this control variable is what we're interested in. So what's the random thing then that's going to? So kind of what we're interested in is looking at whether or not for these people, right, what's going to vary is whether or not they have a viral load less than 50 over the entirety of the follow-up period, right? And so what's the sample space then? Like, what are the possible values that random variable can take?
0 viral load to.
Well, so we're talking about control, right? So control here is just, is it less than 50 the entire time? So it's basically yes or no. Did they control the entire time or did they not? Yeah. Yeah, but the viral load technically could be 0 to infinity, right? So this is maybe what we're interested in studying. All right. So again, a random variable is a characteristic that will take different values for different elements within a sample. We often denote them X, Y, or Z. They can be discrete, they can be countable or isolated. It doesn't matter. So some examples, right, could be like hospital readmissions after a discharge, right? That can technically take values 0 to infinity. It's unlikely that someone's probably going to get to 1,000 readmissions, but theoretically you can picture it. Or that kind of virological control. Are they controlling the HIV? Is it less than 50? Or is it less than whatever the lower bound of the machine is? They can also be continuous, right? So these are uncountable. So there's like age, right? You can say, if you actually look at like a really granularly the days, it could be BMI, it could be viral load, CD4, or say maybe the recovery time after surgery. Right. Any questions on that? Does that kind of make sense for everybody? All right. So a probability mass function. So this is something that basically maps every possible value of a discrete variable. So discrete, remember, means like countable. There's like a set amount of things it can take to some probability. So there's like a one-to-one mapping where it's like that person, we observed 3. Well, the probability of 3 is blank in this data set. While a density function is more about like a continuous random variable, and you're looking at whether or not the probability is some area under the curve of some random variable, some density function. And we're going to get into this a little bit more. So these probability mass functions are usually denoted as kind of this f, y of y, which maps the value of, say, this little case y, which is what you've observed, of some larger random variable to some probability. So it basically means what's the probability that y is equal to yi? All right. It has to be between 0 and 1. You can't have negative probabilities. You can't have probabilities greater than 100%. And also it has to sum to 1. If you sum up over the entire possibilities, it should equal to 1. Okay. All right. So this is an example. So let's say we have our population of babies born at Duke Regional, which I think that's the one up on Duke, right? Duke Ave. And we have to say the number of babies with type O blood. And we have 4 babies that we got, right? And the random variable is the number of babies out of 4 that had type O blood. So our probability mass function of y is given in this table below, where it says, okay, the probability that 0 of those 4 babies are type O is 0.1. The probability that 1 of those 4 is 0.31. The probability of 2 is 0.36. The probability of 3 is 0.19. And the probability that all 4 are type O is 0.04 probability. Okay? So let's see, are all the properties of a PMF met? So the first one, right, is that they all have to be between 0 and 1, right? And that, we're good there. The other thing is they have to sum up to 1. All right, so I'm going to just copy this into R real quick. And I'm going to put some pluses between them. If you can do this in your head, I'm very proud of you. It's 1, right? It's 100%. So great. It satisfies our conditions. Okay. Yep. All right, so let's say, so a question for everybody in the room and Zoom, what is the probability that, say, all 4 babies have type O blood? Not a trick question, I think. Yeah. Huh? No, so this is, remember, this table is basically telling you how many, like the number of babies that have it, and the probability is listed below that.
Oh, so from 0.04 to 0.36?
Well, so that all 4 babies. Yeah. Yeah, 0.04, right? And so it's 4, there's a 4% probability that all 4 babies have type O. All right. Okay. So what's the probability that at least 2 babies have type O blood? So this involves basically, we sum up, right? So this is saying, okay, it's either there's 2, so that's 0.36, or there's 3 plus 0.19, or there's 4, right? So 0.04. So, and that would be .59. Okay. So another way you can calculate that is because you know that everything has to sum up to 1, that's going to be 1 minus the probability that less than 2 babies have type O blood, right? Yeah, so we can go, okay, well, what's 1 minus 0.1 minus 0.31? And we get 0.59 again, right? So if you think about with these probability mass functions, we basically have a giant, circle or, rectangle that the area sums to 1, right? And then we have all these different divisions or separate little areas that define events that happen in there. So 0 babies, 1 baby, 2 babies, 3 babies. And so like you could kind of subtract out being like, okay, we know that one, you know, that has to sum up to 1. So if it doesn't happen, what does that mean? So if you take those elements out, you kind of subtract and you can kind of get at it. All right. So what's the probability that between 1 and 3 babies have type O blood? So here, right, it's going to be 0.31 plus 0.36 plus 0.19. Or you can say, okay, well, that means 1, 2, or 3. So that means there's not 0 babies and there's not 4 babies. So it could be like 1 minus 0.14, so 0.86, which can be easier to add than adding up 0.31, 0.36, 0.19. Okay. Any questions on that? Make sense? Questions on Zoom? Okay. All right. So a probability density function, we have the same notation, but it basically maps some kind of interval of y values to the area under a curve. And it's basically the probability that y falls within that interval. It has some similar properties. It has to be greater than or equal to 0. It has to integrate. So people remember calculus or dread it. You know, we have to say, okay, it integrates from negative infinity to infinity to 1. It's kind of this a 1-to-1 with that summation of the probability space has to equal to 1. And the probability that y is in between a and b is the integral from a to b of fy, y dy. So as a caution for a truly continuous variable, the probability that y is between a and a is 0. So the probability that it takes a distinct value is 0 within the space. So there's no basically area under a curve for a single value. Okay. Also, the inequalities doesn't really matter for a continuous variable. So the probability that a is less than or equal to y less than or equal to b is the same as probability of a less than or equal to y less than b, which is equal to so on and so on, right? Which isn't the case for discrete variables. Okay. So if we were looking at, say, individuals who've acquired, say, an HIV-associated fungal infection, and we wanted to know what their survival time, our random sample would maybe say be 1 individual, and our random variable would be some survival time in days after acquiring. Oh, sorry, I forgot about the expectation of variation parts of this. I apologize. So we're going to step back and go back to the probability mass function. I apologize, people. I forget these things look so nice, but then I forget about the tabs within the tops. All right, so we're going to go back to expectation. Sorry about that, everyone on Zoom. All right, so we're going back to the density function. We're going back to the density function. Okay, so the expected value of y is kind of the population mean. So typically what people write is they write mu is equal to e, and they e, like statisticians see that, and they say expectation. They just see it as that, and to go expectation of y, and it's the summation over all possible values of yi times the probability of observing that. And that'll give the expected value of whatever your y is of interest. So basically, if we measure the change, say, of some CD4 counts from baseline to year 1, in that case 2, the expected value of that would be mu. So if we look at that data set, go in here, go into expectations. All right, so we're going to take this case 2. We're going to filter and drop those that are missing. We're going to just take if the time points are 0 and 2. So I think I did year 2 here. And we're going to group by SID, filter to where they have 2 values. So they have to have both a time 0 and a time 2. Select the variables of interest. I'm going to arrange by t-value, and then I'm going to take the difference, right? So I'm going to show what this looks like real quick. So we can see, all right, and then I'm going to basically slice filter where study is 1. Okay. So at baseline, they had a CD4 count of 194. Later on, they had a count of 392, which gives a difference of 198. Right? And these were just basically making sure that they agreed with each other. So this is another way you could do it, where you pivot wider the CD4 values in the names. So if we look at this, we basically have 1, we have the difference, then we have the CD4 chain, right? The same value, time point 0, time point 2. And then this shows the log fold change, which is sometimes of interest. Okay. And then we can do like a histogram of that to see kind of what the observed change looks like. And the idea is, you know, we can look at maybe the expectation. Okay. And this shows on the log fold change difference. Okay. All right. All right, so the variance is, again, it's a measure of some spread of the data around that expectation. So what it's typically written as is it's the expected value of y squared minus the expected value of y squared. There's a little distinction there where I put the squared. So you can see this isn't going to necessarily equal this all the time. Okay. So we're going to calculate this for this baby example now. So for the number of babies out of 4 with type O blood, we had our probability mass function, right? So the expected value of y is going to be summation over all these of yi times that probability. So we have 0 times 0.1, 1 times 0.31, 2 times 0.36, 3 times 0.19, plus 4 times 0.04. Right? So the expected number of babies out of 4 that will have type O blood, we would, you know, if we had out of a sample of 4 babies, we would expect 1.76 of them to have type O, to have blood type O. All right. Now, if we wanted to calculate the expectation of y squared, this is often sometimes called the second moment, is what people will say that is. You ever hear someone say that? This is usually what they're referring to. So it's the same thing, but now we have yi squared, right? So that's going to be the same for these first two. But for these other ones, right, we now have 4, we have 9, and we have 16. So this is going to come out to 4.1 when we sum it up. Okay. So then the variance is going to be written as, our estimate of the variance is going to be expected value, the second moment minus the first moment squared, which is going to come out to 1.0024. Is kind of our measure of variance of this data. Any questions on that? I'm going to talk about the binomial distribution if there's not. All good on Zoom? Can I get a thumbs up? There is, just in case. Okay, great. Thank you. All right. So binomial distribution. So this is probably the most common, right? One of the, next to the normal, kind of one of the more common distributions out there. So the idea is we have some fixed number of independent trials. So it could be like a coin toss, right? People often use coin tosses for this, or a roll of the die. Each trial is either, you know, some event or a failure. And the probability of success has to be the same for each trial. So if I have a fair coin, if I have a coin, right, the probability of me getting heads should stay the same from flip 1 to flip 2 to flip 3. Right? And they usually denote this as pi. And then the random variable is the total number of successes that you see out of those trials that you did. So if I flip a coin 10 times, how many times, like, am I getting heads? So how it's written is in this binomial function here, which is at times pi to the y, which is y is the number of successes, times the probability of not getting that, raised to the n minus y. So, and this is written as n summation point y. So this is basically n factorial times y factorial n minus y factorial. So what that is basically, so n factorial is basically, so if we said like 3 factorial is equal to 3 times 2 times 1, 4 factorial is equal to 4 times 3 times 2 times 1, and so on, right? And so basically this is kind of a way to divide up, like, all right, because once you get into, say, you have 10, there's multiple different ways, right? You can get 5 out of 10, right? Like the first 5 could give you a 10, then the next 5 could give you a 10. The first one could give you a negative, and the next 5 give you a positive, and so on. So this is kind of a way to calculate and quantify that. It's often used like choose, is the way people kind of, when they see this n y, they say n choose y. How many ways out of 10 trials is there to get 5 heads? And in R, we can get at that. Choose 10, 5. There's 252 ways, right? We don't want to count all those by hand. So I think that's right. Let's see, factorial. Factorial 10 divided by factorial 5 times 1 over factorial 5, right? 252. Right, so I have 10, I have 5, and then I have 10 minus 5 factorial. So now if there's, how many ways is there to get all 10? There's only one way, right? Once you get in that middle, there's lots of different ways these things can happen. All right. So the expectation, if you actually wrote it out and did that kind of what we did for the PMF, is going to be n times pi. So the number of trials that you have times the probability of observing a positive, of observing the event. And then the variance of y is n pi times 1 minus pi. And so when n is equal to 1, this is something called a Bernoulli trial. It's I think, an Italian gentleman. So, and a binomial is basically can be thought of as a sum of independent Bernoulli trials. Okay. Any questions on the binomial distribution or the Bernoulli distribution? No? Okay. All right, so how do we do this in R then? So all the distributions in R have kind of a corresponding density function, a distribution function, a quantile function, and some random number generator. So if we have y is coming from so this means from a binomial, this is distributed as a binomial distribution with n equal to size and p equals to prob. These are what kind of these functions do. So d binom is basically going to say, what is the probability that you had X event? So for our coin toss, right, it would say, okay, if we said, what's the probability of observing 4 heads and, you know, a coin toss of 10, it would give us that probability. So if we go in here and go d binom, I'm going to go X equals 4, size equals 10, and we'll assume it's a fair coin, right? So 0.5. It's going to tell us it's 20% probability, right? So if we said 5, it's going to say it's 24%. And we can basically, so if you remember, we can look at this equation. And remember, we saw this 252. So we should, if I do choose 10, 5, times 0.5 raised to the 5th times 0.5 raised to the 5th, right? Because 1 minus 0.5 is 0.5. We get that value, right? So d norm is just kind of quickly calculating these functions, these values for us. Okay. P binom will give you the probability of observing, say, less than the value that you give it. So if we went back here and we said P binom 4, whoop, Q, it's giving us the probability of observing less than 4 or less. So we could recalculate this and say we did. So basically, actually, if you put in 0 to 4, so if I pass in a vector there, right, it's going to give me the probability of each of these. So it's giving me the probability of 0, probability of 1, probability of 2, probability of 3, and probability of 4. And then if I sum over this, I get that 0.3769531, which is what that P binom gave us. Q binom kind of will return the value that gives you the probability that you want. So if I said Q binom 0. Let's see, type this in. Oops, forgot the size. Prob equals 0.5. It's going to give me 4 here. So this is going to be basically such that the y is less than or equal to that is equal to Q. And then R binom will generate random data from it. So if we do R binom, I'm going to tell it give me 2, size is equal to 10, prob is equal to 0.5. It's going to give me 2 random variables. Okay. Any questions on the probability mass functions? No? Good. All right. So now we'll go on into the random variables. Okay. Sorry, I was a little confused about why this is giving 4 and not 5. But maybe I'll return to this. Think about this a little bit. Anyway. Okay. So next up, right? So we talked about these examples. So we're gonna basically look at the survival time and look at some random variables. So the PDF, the probability density function of survival time in days, is this function 1/20 e being the exponential, negative y divided by 20, and y can be anywhere between 0 and infinity, right? In terms of survival, right? Someone could survive 0 days, or they could survive hypothetically to infinity, right? So we can look at that, and this is kind of what that PDF looks like. You can see kind of the mass, and then as you get further out to infinity and further out, it's approaching 0, right? It's never going to reach 0, but it's going to get, negative 10 to the negative 100. Okay, so first we have to see, are the properties of a PDF met? So the way that you can do this in R is you basically use this function integrate to, right, so we have our function here. So this is how that plot was made that I just showed you. So we're going to go in here. So I don't know why I copied it, because it's all right in here. So this will give us our function and the density, right? And if we extended this out further, we did to 1,000, So there's some weird computational thing going on here. I don't know what that is. That shouldn't be happening. But you can see it's kind of basically 0 after a certain point. Okay. So we have to see whether or not it integrates to 1. So there's a function in R called integrate, where you pass it a function, you pass it the lower limit, you pass it the upper limit. So you don't have to remember like your calculus rules for how to integrate a function. So we run that. Integrates to basically 1. It's not going to be exact because there's some computational error going on in the back. So you can see it's 1.000001. So it satisfies the condition, right? And it's greater than 0 for all values. I don't know exactly what's going on here. I think that's some kind of coding weirdness. Let me see. 260. Yeah, that's some kind of weird dip there. That shouldn't be happening. Okay. Any questions on that? All right. So next up, we're going to say, all right, what is the probability that the person will survive less than 5 days? Right. So we're going to look at the probability that y is less than or equal to 5. So what that's doing is we're taking this density function and we're shading in this gray area between 0 and 5, right? And we're calculating the area under that part of the curve. And that's going to give us the probability that this survive less than 5 days. So how does that look in R? We can just do integrate f is equal to fy, lower equals 0, upper equals 5. And that'll give us 0.221192 with some absolute error. And then if you wanted to plot this, this is using base R. We can, basically add this little polygon in there, this little bit here, which kind of adds the gray. Oh, I forgot that I had the 1000 up here. Hold on, let me go back. And here we go. Yeah, so you can see it's kind of shaded in there. Okay, so if we want to know whether or not the person will survive between 5 and 15 days, it's going to be integrate f of y, lower 5, upper 15. And that's going to give us 0.306, right? So another way you can calculate this, if you think about it, is you can do 0.15 minus 0.5. Oops. Oh yeah, sorry, let me see. Value, okay. Sorry, you always have to check. Sometimes they don't return just a single value, right? So basically, if you can take, say, if you integrate from 0 to 15 and subtract out the part from 0 to 5, you'll get this value as well. And what we're looking at is basically the area under the curve in that gray area. All right. So 15 days, right? So it's basically we're integrating from f of y from 15 upper equals infinity. Can anyone think of another way we could have calculated that based on what we know that everything has to sum to 1? So basically what we could do, right, is because, all right, so let's look at this, right? So we're interested in this gray area, right? And we know that when we integrate underneath this curve, it has to go to 1. So if we're interested in this area, another way we could calculate it is basically doing 1 minus this area, right? So if we do, say, 1 minus, integrate from 0 to 0 to 15. Oh, I forget the value part. These should give the same value. right? Okay. All right, so how about we take another break right now? We'll come back in about 5-10 minutes. Sound good? All right. Recording. And we'll try to see how far we get in this. We may have to finish this off tomorrow. Okay. So we've looked at the probability, all that different stuff, right? And looked at how it's just basically the area under different parts of the curve. So we're going to move into now expectation. What's the expectation now for a continuous variable? So the expected value of y, kind of the population mean, is defined as you integrate over that function from negative to infinity, but now you have y times the probability mass function. So very similar to what we saw, sorry, probability function. Very similar to what we observed for the probability mass function, right? Where it was y times that value, but summing, right? Now we're integrating. And so this is over all possible values. And so then the variance is basically is integral of y minus mu squared, and it turns out to be, it's the same thing as for the discrete, right? It's the second moment, the expected value of y squared minus the expected value of y squared, right? And then the standard deviation is the square root of that variance. We say positive square root, right? Because you have negative times a negative is positive. Okay. So we're going to look at that function again, and we're going to look at these survival time, and we're going to try to see what the expected survival time is. So if you worked out the math, you can actually integrate this as a closed form. I can't remember the solution, like some of the approaches, but it turns out it comes out to negative y plus 20 e to the negative y 20 0 to infinity, which is equal to 20. And so we can calculate that in R. You could also go to Wolfram Alpha. I think we'll do stuff for you. People know Wolfram Alpha. Okay, so I'm going to make this new function EY fun, which is function y, where it's y times the density function. All right. So now when I type in a value, it gives something back. And we say, all right, I want you to integrate that from 0 to infinity. It's going to give me 20 with some absolute error. All right, so the expected survival time in days after getting this infection is 20. All right. If we wanted to then calculate the standard error, it works out to, if you did the closed form of the integral, let me see if this will show up nicely. So the expected value of y squared will write out and comes out to be equal to negative of y squared plus 40y plus 800 e to the negative y over 20, which comes out to 800. So if we wanted to calculate that, we can make another function, right? EY2 fun, which is equal to y squared times 1 over 20 times exponential negative y to the 20. And we integrate that from 0 to infinity, gives us a value of 800. And then our sigma squared is just going to be 800 minus 20 squared, which comes out to 400, right? So our standard deviation is 20. Now, if you wanted to do that in one fell swoop, you could write the variance function based on the fact that we know the mean is 20. So we can say y minus 20 squared times 1 over 20 times the expectation. And if we integrate that from 0 to infinity, it gives us a value of 400. Okay. Often, right, we're never really calculating this by hand. We're always just kind of using sample variance estimates, or a lot of these are from known distributions where the variance and mean has been defined and studied. So they're just kind of easy to kind of just pick out. Okay. Any questions? All right. So let's go to the normal distribution there. So this is often also known as kind of the Gaussian distribution, kind of most widely used. People often kind of assume that things are approximately normal. So like age, height, blood pressure, GFR, lipids, and various others. It's basically a good approximation of what is happening naturally. And also the limiting distribution. So when I say limiting, what that means is that n goes to infinity. As your sample size goes to infinity, many distributions converge to a normal. They basically become a normal. So, for example, like if you have a binomial, that's going to kind of converge to a normal with sufficiently large n. All right? So the probability density function for a PDF with mean, mu, expectation, and variance sigma squared is 1 over square root of 2 pi sigma squared times exponential -1/2 y minus mu sigma squared. All right? And we write that y is normally distributed with mean 0 and variance sigma squared. It's going to be bell-shaped. It's going to be symmetric about mu. And these two parameters, mu and sigma squared, describe a normal distribution completely. We don't need anything else. Any questions on that? No? Okay. So let's make some normals. So we're going to make a couple different ones with different means and different standard deviations and kind of see what they all look like. So pop this out. A little nicer. So this black line is the standard normal. So mean 0, variance 1. This red is a normal with mean 10 and variance 4. So you can see it's a little bit more spread out, right? It has a higher variance. The blue is a normal with mean 10 and variance 16. So that's the same central location, right? It has the same mean as the red, but it's a lot wider because it has a higher variance. And finally, this kind of green line is a normal, I think it's about 2. Yeah, 2, but it has a variance of 36. So it's really spread out. Okay. And then something else you often hear is the standard normal, which is basically that black instance up there, where it has a mean 0 and variance 1. This is typically denoted by Z, where there's kind of, is that a phi? I think that's a phi. Is typically used to denote the standard normal PDF. And you can basically write any normal distribution as just a function of a standard normal. So if y follows a normal with mean, mu, and variance sigma squared, then it's basically equal to a standard normal times sigma plus that mean. So this is a really nice kind of property that makes working with normals really, really nice. Okay. All right. In R, we have the same thing. So we have D norm, P norm, Q norm, R norm. So P norm is D norm gives you the height of the normal density at some value. P norm gives you the probability of observing that value or less. Q will give you the value such that the probability that y is less than or equal to that is equal to the probability you give it. And R norm will kind of give you, that should be an N there, not a P, will generate some random sample of normal. Okay. So if we looked at this data, so we say D norm, and we want to know at x equals -1, it's going to tell us the height of that curve is 0.24 at -1. So if we plot this, it's basically saying, all right, there's -1 right here. And then basically where it intersects this line is at 0.24. Okay. All right. So P norm is basically going to give us the probability of observing -1 or less. So we're shading in that area to the left of the red line, right? So if we write this in, 0.1586553. Okay. So because normal is pretty well defined, we don't have to use the integrate function anymore. So I think if we did integrate, we go f equals to d norm, integrate f equals d norm, lower equals -infinity, upper equals -1. This should give, it gives the same value, right? And what this is doing, as I said, is just kind of taking this and shading it, estimating that area under that curve. Right. So Q norm will kind of give us what is the value on the x-axis that gives us that probability. So if we wanted to say what we want to know at the height of 0.16, it'll tell us that that happens at x equal to -0.9944579. So what this is doing is saying, okay, where is that red line kind of besides -0.9945? So it's not exact. So I think if we put in this should give us -0.1 exactly. Pretty much exactly, right? So -0.99999999998. So basically -1. All right. So I think that's it. So next we have some exercises, but first off, is there any questions so far? On Zoom or in the room? No? No questions on Zoom? All right. Okay, so we're going to go talk about this probability mass function. So we had that babies with type O blood. And let's say it's actually a binomial random variable with 4 trials, right? And the probability of event is 0.44. So that is basically, it follows a binomial with n equals 4 and probability equals to 0.44. So redo some of those questions that we did prior, but now we're going to use the functions in R. So would people like to do these on their own, or should I walk through them, do them at the same time? Walk through them? All right. We will walk through them. So we want to know whether or not all 4 babies have type O blood. Okay. So I'm basically going to go, it is D binom, x equals 4, size equals 4, probability equals 0.44, right? And this, I think, should equal 0.037. So remember, prior it was 0.04. So if we go back up to that original example, find it real quick. Had it as 0.04, right? Which is basically what we're getting. It's 0.03748. Okay, so this is using the D binom function. So at least 2 babies have type O blood. So what we could do here is, right, P binom Q equals 1. Size equals 2. Lower dot tail is true. Prob, sorry, size equals 4. Prob equals, sorry, I have to remember exactly. So for these countable variables, right, the less than and equal stuff does matter. So I just have to remind myself what if it was, if it's strictly less or if it's greater than, if that makes sense. Okay, the quantity x, okay, all right. Okay. So probability equals 0.5, no, 0.44. Lower table. What does that give us? 0.592. See, what was it prior? At least 2 babies have. Type 1, so that was 0.36. So I'm going back and being like, because I just want to make sure. Okay, yeah, so that gives me 0.5, right? So they're about equal. So what I'm doing here is P binom. So the P binom is strictly less than or equal, right? So what I'm saying is, okay, Q is equal to 1. Size is equal to 4, probability is 4, and now I'm saying lower tail equals false. So normally it's going to be less than or equal to that value, but now it's going to be greater than that value. So that was that lower tail equals. So another way I think I could have done this, I did Q binom 1, true, and then I do 1 minus that. It'll give me that 0.5925. Does that make sense, everyone? All right, so next up, we want to know that if there's between 1 and 3 babies have type O blood. So there's a couple different ways to do this. So I'll just kind of go over a couple. So one of the things, the first thing I'm going to do, say, all right, we know that it has to sum up to 1. This basically covers 3 out of the 5 possibilities, right? It doesn't have 0 and 4. So I'm just going to do 1 minus those 2 probabilities. So I'm going to do 1 minus D binom x equals to 0, size equals to 4, prob equals 0.44. And then I'm going to subtract off x equals to 4. Right? So this is going to give me 0.8641. Okay. Another way we could do this is instead of taking away, we could say sum over the possibilities. So that could be D binom. I'm going to just say x1 through 3. So by doing that 1 colon 3, that's basically auto making 1, 2, and 3, if you remember. So another way I could do this is 1, 2, 3. It's going to give me the 3 values. And I could just do sum of that, right? And it'll give me 0.864. So the same value. And I think another way, let's see if I can do this right. So if I do P binom 3, size equals 4, prob equals 0.44, because remember P binom is 3 or less. And I go minus P binom 0, size equals 4, prob equals 0.44. This should give me the same value if I'm, yeah. So this is basically, that third one is being like, all right, it's kind of thinking in the same way as that area under the curve, that shading we were doing, right? Where I'm just like, all right, we want 3 or less, but 1 or more. So if we just subtract out the 0 part, we'll get this value as well. Okay. Now, question for everyone, for x equals to 0, what will p binom and d binom 0? Are they equal? I'm gonna ask someone in the Zoom to write something in the chat. Or not. Okay. So if we do p binom 0, size equals 4. Okay. P binom, size, sorry everyone. P binom 0, size equals 4, prob equals 0.44, 0.09, right? And if we do d binom, it's going to be exactly the same, right? Because there's nothing lower than 0. So they're going to be the same. Okay. Well, p binom of 4 is going to be 1 because there's nothing greater. Okay. All right. So next up, we're going to calculate the expected values of this. So the first thing we're going to do, we're going to use the binom functions. We know what the formula is, right? So we know that it should be, the expectation should be 4 times 0.44 times 1 minus 0.44, right? Did I do this? No, sorry, not the 1 minus. Forget that. Okay, it should be 1.76, right? The variance should be 1 minus 0.44, right? Okay. All right. Sorry about that. All right, so let's calculate the expected value. So the way I'm going to do this is, if you remember, it's the summation of y times the probability, right? So what I'm going to do is I'm going to calculate d binom. I'm going to say x equals 0 through 4. I'm going to say size equals 4, prob equals 0.44. I'm going to throw in a 5 here just to see what it does. I believe it just gives me a 0, right? So if I say, hey, what's the probability that x equals 5 when you have 4 trials? It's going to be, that's not going to happen. Probability 0. Okay. Right, so that gives me the probability. I'm going to multiply it by the x's, the values you can take, right? So 0, 1, 2, 3, 4. So that's going to be 0, 0.309, 0.72, 0.572, 0.14. And then I'm going to sum over this. Okay. And I get 1.76. Okay. We can do basically the same thing for the second moment. Right? So I'm going to copy this, and basically all I'm going to do is I'm going to add a caret, which tells it to square, and I'm going to now sum this. So that's going to give me the second moment, 4.0832, right? So I'm going to do EY, I'm going to define this, AY squared, and now to calculate the variance, we do AY squared minus AY squared. We get 0.9856, right? Which is what this value was. Okay. All right, so next we're going to talk about that, the survival problem that we had, where he's looking at days. So that's what's called a exponential random variable. So exp lambda equals 1 over 20, where the mean is just 1 over that, the 1 over lambda, so which is why it was 20. And so we're going to basically redo this using this function p(exp). Okay. So the function is p(exp), and we go q equals 5, rate equals, I think it's 1 over 20, and it gives us 0.221. Let me double check. (0.2212), right? So it gives the same value. Another way we could have done this is maybe not a way, but you could have done 1 minus, and you say, well, lower tail equals false. It would have done it the opposite way. Okay, so we want to know whether or not now the probability that the person will survive between 5 and 15 days. So here we're going to subtract, we're going to run p(exp) with q equals 15, and then we're going to subtract the p(exp) with q equals to 5 from it. Okay, so we go p(exp), q equals 15, rate equals 1 over 20, minus p(exp), q equals 5, rate equals 1 over 20. We get 0.306, which is what we got before. All right. So they survive at least 15 days. So we can do this 2 ways. We can do 1 minus, right, the probability that they survive less than 15 days, or we can use that lower tail equals false option. We go p(exp), q equals 15, rate equals 1 over 20. We go 1 minus that, or p(exp), q equals 15, rate equals 1 over 20, lower tail equals false. That gives us 0.472. So the probability that someone survives at least 15 days is 47%, which is what we got when we did use the integrate function within R. Okay. All right. So next up, we're going to talk about some QQ plots. So these can kind of help to determine whether or not distributional assumptions are met. So basically, you take your data and you say, you compare it to a normal. And if it should look, the quantiles should be about the same. So you plot the kind of sample quantiles against what would be expected from a normal distribution to try to help you determine whether or not your data is maybe actually normal. So we're going to generate 1,000 samples from a random variable, and we're going to create a QQ plot and add a line to it to check for normality. Okay. Oh, I have to remember how to do this now. Okay. So we're going to basically do QQ norm is the function. So we're going to do YY from R norm. So n equals 10. Sorry, n equals 1,000. It's going to give us 1,000 random normals. Mean equals 4. Mean equals 10. Standard deviation equals 4. Okay. We do QQ norm, YY. It'll give us this normal QQ plot, right? Well, that looks good, but it, is it, if we added a line, does it look okay? So you can see it kind of adds the line. So this data looks pretty normal, which is what we would expect, right? You know, we generated it from a normal distribution. It should be normal. So now we're going to do this, but we're going to do it for the exponential data, right? So I'm going to say y exponential. I'm going to go REXP, like a prescription. Go n equals 10,000, 1,000. Rate equals 1/20. So yours may look a little different because we're not using the same seed, but the general idea is these should look pretty much the same, right? And we can already, I mean, like, we don't even have to do it for this one. I mean, if we just looked at the histogram, right, it's like, well, that doesn't look normal. But let's use the QQ norm. So your QQ norm, YEXP, then QQ line, YEXP. Sorry. So that doesn't look good. So this is suggesting this data is not normal, right? Because it's not falling on the line. So this is a nice way to kind of check, like, your your data to see, like, is it actually normal? Okay. All right. Any other additional comments, I guess, on that? Sound good? All right. So next up, all right, yeah, we're not going to get through all this. All right, so we'll talk about some parameters, statistics, and sampling distribution. So a sample statistic is basically any value that you calculate from your sample. So mean, median, standard deviation, what's the maximum, what's the minimum, what's the IQ, the interquartile range. And their population analog is called like a parameter. So, you can't actually estimate the mean parameter, you can estimate some mean samples, your mean of your sample. So we generally, we try to draw conclusions about that population parameter of interest by using some statistic calculated from the sample. So for that case one, let's say this is case number one, a researcher wants to know the mean BMI amongst the target population. So that's going to be the population mean. They sample 2,500 individuals. They measure the BMI and calculate the sample mean. The person they then use the sample mean to try to draw inference about their population. So in case number two, say a researcher wants to know the prevalence of virological control amongst some target population. So that is population proportion, like how many what's the proportion of them that are controlling virology? They're having virological control. They sample 320 people. They count how many have virological control over some follow-up period, and that is their sample proportion. They then use that sample proportion to draw inference on the population mean. So as we talked about, the population mean is defined usually as the expected value of some random variable, typically denoted as mu. And the population variance, right, is sigma squared, which is the variance of y. And then we have population percentiles, which are basically some value such that the probability that a random variable is less than that is equal to 100 times p, or whatever that is. And that can be calculated different ways. So if you look at like quantile function in R, I think there's like 8 different ways that it can give you the quantiles. So there's different approaches even for that. So statistics are basically random variables. So any value we calculate from some sample is going to be a sample statistic. And so if we draw a different sample, we're going to get a different value of statistic. So multiple samples of the population are going to yield multiple different values of that statistic of interest. Because of this, the statistic is going to be a random variable. So considering kind of all the possibilities of the statistic is considered kind of one possible value of all possible values that statistic could take with repeated samples. So repeating some, sampling, that kind of gives you an idea of what it overall will be. And then these random variables, these like sample means, also have their own probability distributions and probability mass functions. So again, statistics are random variables, and statistics have probability distributions. Okay. So the PMF or PDF of statistic from a sample size n is called the sampling distribution of that statistic, and it kind of describes how the statistic will vary from sample to sample. So if y1 through yn are a random sample for some distribution, say like a binomial or a normal, each yi has the same potential population distribution with some set of parameters, right? So any statistic created from that sample, say y bar, the sample mean, or s squared, the sample deviation, will also have its own population distribution. And that's going to be denoted fy bar. And f of y is not going to be equal to f of y bar, right? So the PDF of y bar is going to be the sampling distribution of the mean. The PDF of the random variable s squared is going to be the sample distribution of the variance. The PDF of, say, capital N is the sampling distribution of the median. These are all going to have different sampling distributions than, say, the overall f of y. So, as a note, the standard deviation of a sampling distribution is going to be called the standard error. So the standard deviation, right, is some measure of the spread about the mean of either the sample or population. The standard error, however, is a specific measure of spread about the mean, but how values of a statistic kind of maybe vary about the mean. So the standard deviation of the random variable y bar is going to be the standard error of the mean, and so on and so on. All right, so for a sampling distribution of the sampling mean, we have a random variable y that has some probability distribution with population mean and some population variance sigma squared. So we have y follows some distribution f of y. We take some random sample, and they're all IID, which means independently, identically distributed from that distribution. So if we have a random variable interest y as, say, cocaine use, which is a binary variable, from the target population, it has some distribution mean mu and, say, variance sigma squared, likely 0 or 1, right? It's probably a probability. So we randomly sample n individuals and we assess cocaine use for each of them. This is a random sample of y. The yi's are independent of each other and they follow the same distribution. For the biological control, right, we have a similar thing. So the target population y, it maybe follows a Bernoulli distribution that has some mean mu, right, which is the probability of controlling the HIV virus. We sample these in patients, and this is going to be a random sample of y's, and the yi's are going to be independent of each other, and they will all follow the same distribution. So we can compute the sample mean y bar. The y bar often will have some a separate sampling distribution with, say, population mean mu and a population variance of sigma squared divided by n. So sometimes f of y bar could be equal to f of y, but typically the variance is going to be written as sigma squared divided by n. It is the variance of this. So for case 1, the sample mean cocaine use proportion has some distribution f of y bar with population mean mu and population variance sigma squared divided by n. For case number 2, the population mean for a binary variable coded as 0 and 1 is the sample proportion. The sample proportion of individuals with biological control will have a population mean pi and a population mean variance pi times 1 minus pi. Okay. Any questions so far on that? getting into more just text. So, okay. So let's say that each sample follows from like S1 through S500, follows some distribution with mean mu. When we take a mean of that, this is going to give us a random sample. So the mean and variance of the random sample of X is defined as, so X bar, right, is 1 over 500, summation of the Xi's. And S squared, the sample, is going to be 1 over 500 minus 1, summation. And I think talked about why the 1 over n minus 1 in last week, right, gives an unbiased estimate. So if y1 through yn are all IID normal, mean mu, then y bar will also be mean normal with mean mu, but variance sigma squared over n. So if the distribution of the underlying population of the random sample is normal, then the sampling distribution of the sample mean will also be normal. So we'll get to this in a little bit. And even when the distribution of, say, the random sample is not normal, the central limit theorem, CLT, will say that the sampling distribution of the mean is approximately normal for large enough n. So for y1 through yn, if it's a random sample from any distribution and it has a defined variance of non-zero, then the y bar, our sample mean, will be approximately normal for sufficiently large n. So go into some code to kind of highlight this. Find it. All right. So we're gonna first, I'll just plot all this so we can see what it looks like. So this is gonna be like the 4 different PDFs, right? So this is a PDF of a normal, 0, 1, see it's bell-shaped. This is a PDF of what's called a chi-squared distribution with 3 degrees of freedom. Here's a PDF of an exponential with a rate of 1, and here's a Bernoulli, right? Where there's a probability of 0.8, it's up here, and 0.2 down here. Okay. And if basically we rerun and calculate the mean over and over and over again, we will get basically a normal distribution. So what I'm going to do is I'm going to say number of replicates, so not the sample size. So I'm going to pull 500 random samples of size 100 from some population. Okay. So the way I'm going to do this is a little bit cheating, but basically I'm going to fill up this matrix of size with 100 rows, and I'm going to, and it's going to have 500 columns, right? Oh, let me run this. So this is going to basically be, no, I thought I ran this. So if we look at this, 100 by 500, right? And we're going to take the column means of this. So basically, I'm treating each column of this as like it's a replicate of our study. So column means, you can also use the apply function and mean, but we're going to take the mean. So we got YB norm, take that. All right, so next up, we're going to do a chi-squared. So the same thing, it has this R chi-squared. I'm going to say degrees of freedom equals 3, number of rows 100. I'll give me this, right? Everyone following along with this so far? Okay. We'll do this for an exponential. So what I'm doing is, right, I'm just calculating the mean over a bunch of different trials of this to kind of show that it's going to be normal. And then I'm going to get some theoretical quantiles, and we're now going to plot this. So I'm just going to run this all at once. This is not, figure margins too large. Okay, well, anyway, this is kind of what it looks like in the plot run. So this shows the y bar of, say, a normal. This is the y bar of the chi-squared. This is going to be of the exponential. And this is of the Bernoulli. Okay, so you can see they all are relatively bell-shaped. They're not perfect, but they're definitely approaching normality. All right. So if we redid this with like 1,000, I can get this to work. All right. So figure margin's too large. Maybe that'll fix it. Okay. I'm just gonna. So this shows the normal, right? Looks pretty good. Let's look at the chi-squared. Why is it cut off like that? All right, let me just plot this over in this one. That's what happens when you go off script. Okay, so it's being cut off a little bit at the top. Let me just bump this up, that's why. Okay, it's really being bumped off at the top. Because I changed the density. Okay. It looks bell-shaped, right? It looks like it's standard, kind of a normal. Right? Which is great. And this should be 1,000 actually now. Right? Because now n is equal to 1,000. So you can see it looks really, so the blue line is what the normal with the mean 3, which is the mean of a chi-squared, degrees of freedom 3. And the standard deviation equals the square root of 6 divided by 1,000. So you can see, like, once you get sufficiently large n, these population means are going to look normal. So what is sufficiently large? It really depends. It depends on also how non-normal the data is. Like if it's really, really skewed, it may require a much larger n. If they're already continuous or relatively symmetric or bell-shaped, you may not need a large one. So the rule of thumb that people may have heard of n is equal to greater than 30 maybe doesn't apply. You really have to know the data and kind of look at it and look at the bell, like, and see what's going on. So know the data, make these plots, look at the histograms, look at QQ plots, and to try to get an idea whether or not you feel comfortable making that assumption. Okay. Yeah, and I skipped over this plot, but it also just shows the QQ plots of those means. And you can see they line up pretty much perfectly. Okay. Any questions on that? All right, so I think maybe what we'll do is walk through these exercises, and then we will basically maybe call it, and then maybe next week we'll go over confidence intervals and do case study. Sound good? Yep. Okay. So we're going to kind of redo what I was kind of talking about. We're going to create a matrix size 100 by 500 generated from a normal distribution with some mean mu and some variance. We'll set a seed just so that we can, get an idea of what's going on. So that we all have kind of the same values. Okay, so I use 2894. So what I'm going to do is I'm going to say big math I'm going to do matrix R norm. Then how many did I say? 500. 100 times 500. Anybody have a mean that they want to use? Was it?
31.
31. Okay. And we'll do a standard deviation of, oh, wait, I'm in the wrong spot. Okay, here we go. Mean, and then we'll do standard deviation of 6. All right, I'll go number of row equal 100, right? So this is going to give us a big matrix that is 100 by 500, where each row represents each column represents a replicate of the study, let's say. All right. So next we're going to get the mean of each of those studies. Okay. So we can use that call means function that we talked about. You call means. I'm going to go big map. And that's going to give us a vector size 500. Right? And it's just going to be the mean across all of them. So you could also do this via apply big map to mean. Right? And it should give exactly the same thing. So what I'm doing here is I'm subtracting the two, and the range of the differences should be 0 to 0 because they're the same. All right. Now we're going to calculate the mean and variance of this. So what should the mean be? It should be basically 31, right? So it's 30.98628, right? It's very close to 31. Now we're going to calculate the variance. That's 0.354034, right? So remember the standard deviation was 6. So this is going to be, so this should be equal to 6 squared divided by 100. Pretty close, right? 0.36 versus 0.355, right? So very much kind of on the money. Now let's do this for a random binomial, right? So we're going to, for Bernoulli. So we're going to generate a big Bernoulli, big Bern. We're going to do matrix. We're going to do R binom. Go n equals 100 times 500. Size equals 1. We'll do prob equals 0.78. We'll go number of rows equals 100. Okay. So this is going to give us 100 by 500, right? So we're going to calculate the mean. So what I'm doing here is a snippet. It's like an R code snippet. So it's just like a fast key that I made to put something up. So if people are interested, you go to tools, global options, code, snippets, and you can make your own snippets. But I like it because then I can just get this kind of comment thing that I like. Sorry, that's an aside, completely separate. But all right, calculate the mean. So I go call means, big Bern means. So when we calculate the mean of this, right, it should be 0.78. It should be very close. So mean, burn means 0.77918, right? Very close. And when we calculate the variance, it should be 0.78 times 0.7 times 1 minus 0.78 divided by 100. So we do that. Comes out to 0.0018166761. So let's see if that matches up with what we think it should be. So we do 0.78 times 1 minus 0.78 and divide by 100. Very similar. Not exact, but very similar. So the values changed there because I didn't set a seed in this example. But you can see it doesn't really matter because, you know, they're going to come towards the same thing. Okay. Well, so that gets us to basically it. I don't think I can run through confidence intervals in 13 minutes. So yeah, if anybody has any questions at the moment, let me know. Any questions in the chat or in the room? No? All right. So while people are thinking about whether or not they have questions, I'll put up the survey. Hopefully this works. So there's the QR code, the link. Just go to today. But yeah, if anybody has any questions, let me know. I can try to answer to the best of my abilities.